Part two, let's go. Let's do some stuff with some vectors. Right to it. Bam! Here's what we're going to look at in this video. We are going to see how to normalize vectors, so how to take a vector and rescale it so that the new form of it has a length of 1. We are going to look at two different ways to multiply vectors. There are others, but two for now. And I want to unpack a little bit more this idea of dimension and connect that back to some of the span and basis stuff from the last video. All right. Speaking of, now this is pretty much a rehash of what I said last time. I trimmed it down a little bit just to the core essentials, but we want to say that if you have a set of vectors, then you can make linear combinations of those vectors. And every vector that is created by those linear combinations builds up a space, and that is the space spanned by your set of vectors that you started with. Then a basis is a set of vectors that span a space and are linearly independent of each other. We'll come back to this, but first, what's this hat business? X hat, Y hat in the middle line here. Well, these hats are some notation, and they mean that the quantity labeled with the hat is a unit vector. It has a length of 1, a magnitude of 1. The way you write this is the notation. So you have double vertical bars, boop, boop, and then x hat, double bars, boop, boop, equals 1. So this means the magnitude of the vector x hat is 1. That's how you would say that in words. Now, in order to take any vector and turn it into a unit vector, you need to divide it by its own magnitude. If I have a vector that has a length of 3, and then I divide it by 3, the new vector has a length of 1. It's actually not that mind-blowing if you just say out the logic like that. X vector has a length of 3, the magnitude of x is 3, I divide them. Now I get something that has the same direction as x, but it is 3 times shorter. It only has a length of 1 now instead of a length of 3. All right, so that's unit vectors. And we label them with hats because knowing that something is a unit vector lets you do easier math, because when things are ones and you're multiplying by ones, then it saves you trouble. Okay, but what's the magnitude of a vector? I keep saying magnitude, length, just kind of casually, but there is a more thorough and more general definition. And to go big here, the norm of a vector is the most general, mathematically correct word for this quantity that I'm introducing. It's the how muchness of a vector. When our vectors are magnitude and direction in a space, when it's some physical arrow that points in a certain direction and that arrow has some length, then yeah, that thing has a magnitude. But other kinds of vector spaces, let me go back to the example from yesterday, the music example. You have your catalog of songs, and those songs have different attributes. And you can write a vector that describes the attributes of a song. Things like, what is its, is it fast or slow? Is it syncopated or straight? Is it orchestral, or is it electronic, or is it on acoustic instruments or electric, blah blah blah. Like, you have all these attributes that can be quantified, and so you have this vector of things that doesn't have a direction. It's not like this is some physical space where these attributes indicate left and right and up. They're describing other attributes of the song that are not geometric ones. So this is why this idea of a norm is important. When your vectors are not arrows in a direction, but are instead collections of components that tell you attributes of the quantity being described, then the norm tells you the total size of the vector. Now that I've said all of those words with this slide lingering here, the way you calculate the norm of a vector is you take its inner product with itself, and then you take a square root. So the angle brackets here, these indicate that It is the inner product of x vector with itself. So you take that inner product and then you take the square root of that. This is very analogous to finding the absolute value of a number by squaring that number and then taking its positive square root. And also analogously, when you do this, the norm of a vector is always real and positive unless the unless the vector itself is the zero vector. If the components of x are just 0, 0, 0, 0, 0, 0, 0, then it has a norm of 0. But any non-zero vector will have a positive real norm. This comes down to the properties of the inner product. You're like, what's an inner product? And I'm like, wow, I'm so glad you asked. Let's talk about the inner product. It's turtles all the way down, I'm telling you. Okay. If you get that reference, let me know. I don't know, give you an imaginary cookie or something. So what's an inner product? As we continue down the rabbit hole of vector properties and vector operations, for good old-fashioned magnitude and direction vectors, when we were talking about things that point with some length in a certain direction in a physical XYZ space, the inner product simplifies to the dot product. So I am hoping that you have done dot products before. Here's the formula for the dot product. What you do is you pairwise multiply the corresponding components of the two vectors. So the first component of x times the first component of y. Second component of x times the second component of y. Third component times third component, on and on and on, as many you have. And then you add together all of those multiplied pairs. So that is the dot product. And for starting out, this will be the kind of spaces that we're working in. As we get to other examples, then one of the things when we introduce a new space, like yesterday I floated this idea of complex numbers, for example, when you're working with complex vectors, the inner product has an additional step that you have to do to calculate it. It looks like a dot product mostly, but there's a little bit more going on. We'll get there when we get there. Right now, we will start simple. We'll start with just good old-fashioned real vectors. We will, however, get to more interesting stuff as time goes on. All right. So now we know what a unit vector is. We know how to find the norm of a vector. We know how to normalize a vector. You take the vector, you divide it by its own norm, so it becomes a unit vector. And you find its norm by taking its inner product with itself, which if it is a real vector, just means the vector dot itself, dot product. Now, another property of the dot product that you hopefully have seen before is that it is related to the angle between two vectors. And in 2 dimensions and in 3 dimensions, this angle is exactly what you think it is. You have your 2 arrows, and there's some angle between those 2 arrows. And like, okay, great. Why was that so hard? Well, as you get to higher dimensional spaces, if we're working in a 4 or 5 or 6, whatever dimensional space, then the way you define the angle between 2 vectors is actually with this formula that's on the screen. Because, okay, so pause, tangent, this is not on the test, so to speak, but I do think it's interesting. So here's some brain candy for you. In order to talk about the angle between 2 vectors, like there's a vector, and there is some angle between them. Boop. The way you construct that angle geometrically is first you have to find the plane that contains those 2 vectors. And it is the angle in that plane. If you take one vector, rotate it around in the plane until it lines up with the other vector, that is the angle between them. And in 3 dimensions, this works great as well. I'm not going to try to draw in 3 dimensions on the slide, but if you have some XYZ space, there's an arrow pointed one way, an arrow pointed a different way, there is still a single unique plane that contains those two vectors. And so there is a unique geometric angle between these two things where you take those vectors, you take the plane that they're in, you rotate the vectors around in the plane, they line up, you found your angle. Why am I making a big deal of this? Seems obvious. You have two lines, there's a plane that contains those two lines. That's like high school geometry stuff. Well, in 4 or more dimensions, there is no longer one single plane that contains any two vectors. There can be more than one plane containing those vectors. And so to talk about the plane that contains those lines is no longer meaningful because there is no longer the plane. There's a set of planes. And you're like, which one then? And you avoid this problem by redefining what the angle between things means. So you take these formulas that work in 2 and 3 dimensions and you extend them to higher dimensions through this use of the inner product. Okay, end pause, tangent is over. If you thought that was interesting, great. If not, it's cool, that was bonus content. But operationally, I want you to know that you can calculate the angle between any two vectors. And the way you calculate that angle is to follow the formula on the slide. Take their inner product, divide by the norm of the first vector, divide by the norm of the second vector. And as a result, you get some number between -1 and positive 1. So then the cosine of the angle is that number between negative and positive 1, or equivalently, you can say that the arc cosine of x dot y over xy is theta. Cool. So that's how we find angles. Let me show you an example here. We have two vectors in 3 dimensions, and I'm like, what is the angle between these two things? Well, you use the formula. So first, we are going to find the magnitude of x. So x dot x, square root. 1 squared plus 1 squared plus 3 squared, the sums of the squares of the individual components, that's the length of that vector. This is Pythagorean theorem. And then we need the magnitude of y, so we do the same thing, 0 squared plus -1 squared plus 2 squared, and now we have the lengths of our vectors x and y. So here's x, and here's y. Now that we have their individual magnitudes, we need to calculate their inner product. So first components multiplied, second components multiplied, third components multiplied, add it all together, and we get 0 minus 1 plus 6 equals 5. So the inner product of these two vectors is 5. Now finally, we take all our stuff, plug it into the formula. Numbers go in. I mean, this is just, it's square roots. Like, what are you going to do? Throw it to the calculator, obviously. So cosine of theta is 0.67. You take the inverse cosine, and you find that it's about 47, 48 degrees. Is this exciting? I mean, it's the angle between two vectors. This is not the most thrilling thing that has ever happened, but it is a useful tool that lets you do more interesting stuff once you become proficient with this tool. Now, conceptually, there is one thing I want to highlight before we move on, and this is what you learn just from the sign, the SIGN of the dot product. If the dot product of two vectors, and I'm talking magnitude and direction, spatial vectors, arrows that point a certain way, if the dot product of those vectors is positive, they're mostly aligned with each other. They're generally pointing in the same direction. The angle between them is less than 90 degrees because the cosine of that angle is positive. If the dot product of two vectors is negative, then the opposite is true. That means that they're more or less anti-aligned with each other. They're pointing kind of in opposite directions. Not just different directions, but opposing, because the cosine of the angle between them is between 90 and 180. And then our third case, if the dot product is exactly 0, or I'll say this. If the dot product of two arrows is 0, then that means that they are 90 degrees apart from each other. The cosine of the angle is 0. The angle is exactly 90 degrees. More generally speaking, let's use our fancy new linear algebra language, sound like sophisticated people. If the inner product of the two vectors is 0, that says that they are orthogonal to each other. And you're like, why did we need new words for that? Oh, we're going there, but not today. So that's inner products. There is also kind of, let me just be upfront here. What I'm about to describe isn't actually real. Like, of course, it's a mathematical operation you can do, but it's a simplification of a more broad, more general operation. We're taking one specific case of it that happens to work out really nicely and be useful. So I'm not teaching you a general truth here. I'm teaching you a very specific, narrow concept that is useful in a lot of circumstances. And that is the cross product. If you have seen this before, great. If you haven't, no big deal. But a cross product is a way of multiplying two vectors in 3 dimensions. This only works in 3 dimensions. And this is why I say it's a simplification. It's a special case. Inner product you can do in any number of dimensions. 1 dimension, a billion dimensions, there's an inner product. You're good. Cross products only exist in 3 dimensions. So we write it with the X, the times symbol. That's why it's called a cross product, right? Because this is a little cross on its side. So you have that. And the utility of this is everywhere in physics. It's kind of special to 3 dimensions, but we live in a 3-dimensional world, kind of. Asterisk, asterisk, qualifier. Yeah, kind of, sort of ish. We have 3 spatial dimensions that we inhabit in our everyday lives. And so things that live in 3 dimensions are very often useful for describing the physical world around us. Many vector operations, especially in electricity and magnetism, rely on cross products. So how do you do it? How do you calculate the cross product of 2 vectors? Well, what it produces geometrically is you take the 2 vectors, and again, in 3 dimensions, there is a unique plane containing those 2 vectors. The cross product produces the normal vector to that plane, the vector that is perpendicular to the original 2 vectors pointing out away from them. That's the geometric interpretation of this. As far as calculating the components of that thing, asking like, okay, but what are its x and y and z values? I want you to stare at this image for a second. There is a circular relationship between the x and y and z axes in 3 dimensions that as you go x, y, z, x, y, z, x, y, z, that you're going around a circle in one direction. Because you could also name them in the other direction. You could go y, x, z, y, x, z. Those are 2 different lists of numbers. If you learned any combinatorics stuff in high school, maybe, then this is talking about circular permutations of the coordinates. We have our cross product, A cross B. The x component of the cross product is the y component of the first vector times the z component of the second vector minus the z component of the first vector times the y component of the second vector. And you're like, what does this have to do with the circle, dude? Okay, look at the order of the subscripts. X, Y, Z. That is going in the forward direction around this circle. X, Y, Z. So that gets a positive sign. And then the other term, X, Z, Y, that's going in the backward direction in this circle. That gets a negative sign. What we're going to do is we're going to make all the different pairwise multiplications, yz, zy, zx, xz, xy, yx, and each of those pairs gets either a plus or a negative on it. It gets a plus if it's going forward around the circle, and it gets negative if it's going backward around the circle. If that made sense, great. If it didn't make sense, honestly, spend some time with it. Sometimes I'm like, yeah, it's not a big deal. This idea of permutation and of circularity and of orders of going forward and backwards and things is actually quite important. We will come back to this concept. So I would actually recommend sitting with this for a little while until you see the pattern. You're like, oh, that's what that is. Um, I actually don't have these formulas memorized exactly. Like, of course, if I think hard, I can figure out what they are, but I remember the pattern. I remember the formula. I remember that it's pairwise multiples and that the forward cycles are positive and the negative and the backward cycles are negative. And knowing that rule, I can figure out what all the components are. So, this is one of those cases where if you think harder, you're also actually thinking smarter. Instead of memorizing 9 terms in these equations, you're memorizing 2 rules and then getting the calculations you need from those 2 simple rules. Okay, so why do we care? Well, I already mentioned this. This is the idea of the dot product or the inner product telling us whether vectors are generally aligned or anti-aligned, or whether if their inner product happens to be 0, then they're orthogonal. But in general, this isn't just about arrows pointing in directions. This is about similarities of things. Let me go back to the AI example from the previous video for a second. When we look at a word in a large language model, or better yet, a string of text, then there is some vector encoding that string of text. It's a list of numbers and it's way more than 3. Often these are millions or billions of dimensional spaces. So we've got a vector that's a billion components long, and that represents some string of text. Then we have a different string of text, and that's represented by some other vector that's also a billion numbers long. And you want to ask the question, how similar are these two strings of text to each other? Do they convey basically the same meaning, or do they convey different meanings? Are they unrelated or are they synonymous? You can do that with linear algebra. This is a big part of the reasoning that large language models do when they're calculating responses to user inputs, is they're finding vectors in the space that are semantically aligned with the probable responses to a given prompt. They're doing inner products to see whether the vectors representing these texts are aligned with each other or not. That's not all there is to it, but that's absolutely part of what they're doing calculationally. So it's very cool and it's a very robust and versatile tool. It's not just about angles between arrows, is my point. So I said this yesterday. Now I'm just repeating it now that we have a little bit more of the language unpacked. So we want, when working in a vector space, you've been doing this automatically without ever thinking about it, probably. But when you do X and Y and Z, that is an orthonormal basis of 3-dimensional space. X hat and Y hat and Z hat are unit vectors. It's 1 unit left, right, 1 unit forward, back, 1 unit up, down. They are already normalized and they're orthogonal to each other. It's the inner product of X and Y is 0. They don't have any overlap at all. The inner product of X and Z is 0. They don't have any overlap at all. The inner product of Y and Z is 0. They don't have any overlap at all. So all this stuff that you've done like up to now with vectors and writing X and Y and Z components and so on, you've been following these rules, never maybe knowing that they were rules that you were following. And again, it is not mandatory to do this, but we do this because it makes the math easier. So I said this 3-dimensional space thing, and I've said dimension a couple times today. Formally speaking, the dimension of a space is the number of linearly independent vectors you need to form a basis of that space. So if you're in 3-dimensional space, you need three vectors, three independent vectors in your basis in order to describe any other vector in that space. If I want to know in 2 dimensions, where am I on the surface of the Earth, I need a latitude number and I need a longitude number. That's a 2-dimensional vector space. I have 2 independent vectors, latitude and longitude, and by summing together some combination, some linear combination of latitude and longitude elements, I can describe any position on the surface of the Earth. Lots of other possible examples here. But the dimension of a space is also the number of components that any vector in that space has. Like with my Earth example, every point on the Earth has a latitude and a longitude. It's a 2-dimensional space because you need 2 numbers to describe where things are in that space. And this means that, so now we're starting to look forward, any vector in a space is written as a sum. It is a sum of basis vectors times components. The components of a vector, what they really mean is they mean how do you build that vector out of the underlying basis? How many basis vector ones plus how many basis vector twos plus how many basis vector threes, et cetera, give you the total vector. When we're in 3 dimensions, we usually think of that as how many x's and y's and z's. But in principle, the meanings of those axes can be anything, as I've given some examples today. All right, that is a lot. I'm sorry this went on so long. There's some kind of big brain ideas here, but we will have practice with these things in class. And where this is going in the immediate future is we're going to start talking about matrices, because those are where we get the tools really for manipulating vectors and using them to describe useful physical entities in the universe and how they relate to each other. So please look forward to it. Thank you for your patience. I definitely will not have most of the videos being this long, but every once in a while, there's a topic that just takes more time because not everything can be explained both well and quickly. So thanks for putting up with me, and I'll see you in the next one.